That's right. All right, I got to get this thing. And then I go with that thing. All right, I guess I can do this. Okay, so we talked about the Calvin cycle after Melvin. Melvin, Calvin, Melvin, Calvin. Okay, come on. Do I have to do this? Okay. I want to, I've got my thing. Why can't I put that there? Go blue. Oh, turn it on. What a moron. Finally. Okay. It's alive. Chapter 7, we need to finish this puppy up. Be done with it. And Monday we will have the Chapter 7 discussion question. Exam in the library at the LRC Testing Center. Happen as usual. Okay, I'll try to remember to post all that information. Okay, so we did the Calvin real quickly. I'm just going to kind of review it. They call it the C3 pathway. C3 because your first stable compound is actually a 3-carbon molecule. Now you don't need to write this. You have it. It's in your notes already. C3 pathway. All right, so let's see. We have carbon dioxide that comes into the plant, CO2. It's going to combine with a 5-carbon molecule, which we call RUBP, ribulose bisphosphate. And this is all occurring in the stroma, the fluid of the chloroplast. Okay, and so those two combine right there using an enzyme called Rubisco, and that's probably the most important enzyme on planet Earth because it is the most common. It's the most common, most abundant enzyme. It puts those two things together, and so. Yeah, they typically say the most important enzyme on Earth right there. So we do produce a 6-carbon molecule, but this thing is not stable. It's not going to stay 6 carbon. This is not stable. So it'll break. And it breaks into 2 3-carbon molecules, which are stable. So then we have a 3-carbon here and a 3-carbon here. And they're not just 3 carbons in a row, and that's all you have. You have other things there, hydrogens and some other things. But anyway. And these are PGA, phosphoglycerate, which you should have in your notes. We did this yesterday. But at this point, so that's first stable compound, 3-carbon molecule, first stable, which is why they call it a C3 pathway. All right, PGA, first stable compound. Now, at this point, we're going to use the products that we produced in the light-dependent reactions. We made actually 2 things. We made NADPH2. So we stuck some hydrogens on a carrier, NADP, and we also made some ATP. We made some energy. Now, this is why we made that, because what I want to do is I want to take these 2 hydrogens and I want to put them on that 3-carbon molecule right there. So I'm going to convert NADPH2. I'm going to convert that just back to NADP. And I remove the 2 hydrogens and I put them on that 3-carbon molecule. So I now have a 3-carbon molecule with 2 hydrogens on it. That molecule is called PGAL, and that's listed also in your notes, hopefully from yesterday. That's what we do. But this takes energy to do that, to remove the hydrogens and put them on PGA to make PGAL. So I'm going to break that down into ADP plus PI, and it releases energy. And the energy is used to remove the 2 hydrogens, put the 2 hydrogens on the 3-carbon PGAL, and of course what we formed PGA, and we have formed a molecule of PGAL. Well, I do that again over here as well. So I'm going to take my NADPHT, NADPH2, and I'm going to remove those hydrogens. I'm going to put them on my PGA. That takes energy to do that. So I'm going to take ATP, because those are our 2 products that we manufactured in the light-dependent reaction. I'm going to break the ATP into ADP and PI And I remove the 2 hydrogens off of my NADPH2, and that just leaves me with NADP. Okay, well those hydrogens went on that 3 carbon, so now I have a couple of hydrogens on that 3 carbon. Well, that's my PGAL. So again, PGAL. Okay, so, but this thing happens thousands and thousands and thousands and thousands of times. I don't know. Depends on how much sunlight you have, how much water you have available in order to do the light reaction. So you got to do the light reaction first so you can produce your NADPH2s and your ATP, and that requires light. So if it gets really dark for a long period of time, it gets snowy, and you know, if you're in, say, like Seattle, where it's always, you know, kind of raining a little bit and misting a little bit, and you don't get a lot of sun, those plants are going, I need sun, I need sun. People are going, I want to see the sun. You know, they get really tired of that after a period of time, and we're like, what, you get tired of rain? Yeah, they do. They do. I don't. I'm like, anytime it rains up, even if I've just washed the car, I'm like, rain on that car. Make it muddy. Let's get all the roads muddy. So I have to wash it again. I don't care what. I just go through a robo wash it. Anyway, laser wash. This is clean. You know, get out on the highway about 80 miles an hour. It just kind of takes all the water off of it. You know, you don't have to get out and like do anything. Pretty easy. Shake out your mats. You're ready to go. Anyway, I don't mind rain. Okay, so, but the whole thing about this is we made 2 PGALs, and any two PGALs are used to make sugar. Actually, they make fructose first. They're put together to make fructose, and then that is converted into glucose. So ultimately, we make glucose sugar. Okay, that's what we wanted to do. We wanted to make sugar. That's photosynthesis. Was the deal. Why do we do photosynthesis? We want to make sugar. Did, end of story. You know, you're like, oh, it's kind of anticlimactic. But, you know, hey, we're going to make sure this is the end of the process. Wow, this ought to be like super. And it's like, well, so what? You know, any 2 PGALs. Now, we also have to remake some of these. Eventually, if you did this over and over, you would run out of RUBPs. Now, you can get plenty of CO2 out of the air. That is not a problem. CO2 is very abundant. We keep making it more abundant. So that's certainly not a problem. But we have to regenerate these RUBPs. So some of the PGALs are used to remake, because you're doing this thousands of times. So some PGALs used to remake RUBP. Ta-da. You can do it again. You got plenty of RUBPs. You bring in more carbon dioxide. You do this thing out in the stroma. Slam those 2 together with Rubisco. 6 carbon, it splits. Form your PGA, throw a couple of hydrogens on it, takes the energy ATP, make your PGAL, put those 2 together, and you make your sugar. Use some of the PGALs to remake RUBP. So that is the C3 pathway, also known as the Melvin-Calvin cycle, named after Melvin Calvin, or they just call it Calvin cycle. I mean, some of your products, your PGAL, used to recycle back to make your RUBP, so it is a cycle. Melvin Calvin, poor guy, how tough his life must have been. So he just ended up, you know, all by himself in a lab doing experiments, you know, doing research, because he couldn't deal with society, because his name was Melvin. You know, don't you want to know the real stories on this? You know, get like some hot chick in there. Give me the real story. I want to see the video. Show me the video. Yeah. Oh, am I that sick? Oh, yeah. What? 80% of all internet traffic is porn. you know, that they know what it is. 80% of all internet traffic, 80%, hello? And people are like, oh, well, that's just bad that you'd say that. I'm like, yeah, 80%? Sure. You're going to sit there and look at me? Really? I'm not buying it. That's, I don't know, that's a lot of internet traffic. Really, at 58, you don't even look anymore, seriously. It's like there's a time when you just go, I've seen it. I've seen all of it. Yeah, I've seen every bit. I've seen everybody get everything. I've seen all the crazy things that could ever possibly do. I'm just like, I've seen enough. Okay, quit. Stop. So I'm the other 20% who's using the internet, you know, personally, because I really no longer interesting. They have lost my interest in that completely. All right. Anyway, now that's a C3 plant. Most plants are C3. Most plants are C3 plants. Okay. All right. Some plants are what they call C4 plants. And the C4 plants are growing like crazy. Grow fast. And there's not a huge difference between a C3 plant and a C4 plant. In fact, they're very, 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 very similar, except one little minor change. C4 plants, examples of these things, which would be e.g., that's actually a Latin thing, which means example. And I used to know what it is, but I've forgotten. Example. It's actually e.g., not ex. Ex doesn't mean anything. Exercise. We use that as an abbreviation for an exercise, like in a lab. Example, corn is a C4 plant. Crabgrass. Don't like that stuff. I've got a flower bed and crabgrass in Alpine, and every time I go, I'm out there picking crabgrass. And then I go again, I'm picking crabgrass, you know. That stuff grows like crazy. Also, sugar cane, which is how some places get sugar. That's how Mexico, they use sugar cane to produce sugar. We use sugar beets. Sugar beets. That's where we get our sugar, which has kind of a little not such a great flavor. Sugar cane sugar is like really, really, really sweet. I like it a lot. So sometimes I run out of it, and I ask students if they ever go into Mexico because I'm too scared. I don't want to get killed, you know. Just what? I was over here for sugar. Sure you were, you know. Yeah, what do you really want to buy? You're after our chicks, you know. No. You want our drugs? No. If I really want drugs, I can buy those in the States. Yeah, for myself. I'm kidding. That's a joke. It's not too funny, but it is a joke. Okay. But anyway, these things grow real fast. And corn, okay, as an example, my grandparents had a ranch. They were cattle ranchers in Oklahoma. In fact, they were pretty big-time cattle ranchers in Oklahoma. They had lots and lots of land. And anyway, my grandmother wanted a garden, and so my grandfather tilled up 5 acres and says, there it is. Just plant it. 5 acres, a garden. She didn't have a garden. She had a farm. Anyway, so she would plant corn and all kinds, you name it. She had it in that garden. And you know, within like 2 or 3 months, you'd go from a corn kernel. We all know what a corn kernel is. Put that thing in the ground, cover it up, you know, and they got enough rain there that they didn't have to really irrigate it much. Occasionally they'd irrigate it a little bit. But, you know, that corn kernel would grow, and it would be like 8 feet tall. You'd have an ear of corn on this one stalk. And, of course, these leaves were huge and long, and you'd have several ears of corn that were, say, 8 inches in length. And each one of those ears of corn, I don't know how many corn kernels are on an ear of corn. I've never bothered to count, but you can do that and let me know the approximate number. Let's just say hundreds and hundreds of kernels. And every one of those kernels of corn is packed full of sugar. You eat corn, it's sweet, unless you bite too early and then it's not sweet. It's starch before it actually converts into sugar. But, that's just tons of sugar in every ear, in every kernel. And then you have like 1,000 kernels, for example. I don't know. It could be 750. I have no clue. And you have several ears on this one plant. And all of that happened in a span of 2 to 3 months. Really? A plant can produce that much sugar in a span of 2 to 3 months? Crazy? Crazy? Yeah, crazy. Well, they're C4 plants. Sugar cane grows like a weed, just whoosh, bamboo. Bamboo, my gosh, it's a grass. What, it's like an 8-foot grass? I need a big mower. Yeah, it's bamboo. We don't have it around here. We have some cane plant that grows. I'm not even familiar where that came from or how we got it or why it's here, but it can grow in certain areas. Low-lying areas, typically where water collects, is where you'll find it on sides of highways and things. Anyway, it's a C4 plant. So they're very fast-growing plants, and this is the reason they can do that. So you have the normal C3 process, meaning that, you have a cell that will take a 5-carbon and combine it to the carbon dioxide and combine it to the 5-carbon. We're doing the C3 Calvin cycle. That's what we're doing. So you have the CO2 comes into the plant, it combines to a 5-carbon RUBP, that immediately becomes a 6-carbon, which immediately splits into 2 3-carbons, a 3-carbon and a 3-carbon, and when we convert those, add a couple of hydrogens to them, and you make a 3-carbon with a couple of hydrogens on them. Okay, those are PGALs. I didn't show the NADPH2 coming in here, and the ATP going in here. We need those. But we're just doing the normal, regular Calvin cycle, the C3 pathway. So here's a 3-carbon with a couple of hydrogens on it. Again, that needs to have a place to get your hydrogen, so NADPH2, and that requires energy to make sure that can happen, so we got ATP. All right, so any two of those PGALs are used to make glucose sugar. Nothing new. I didn't do anything new. I just kind of shortened it up a little bit. Kind of did a Reader's Digest version of that thing. And that's C3 path. So here's a C3 pathway. And that's Calvin cycle. All right, this is where it changes though in a C4 plant. In the C4 plant you have another cell in addition to this one. This cell where the C3 pathway occurs, that is called a bundle. It has a name, a bundle sheath cell. Okay, now the other cell that only C4 plants have will be this one. And you don't find those in C3 plants. And this is called a mesophyll, which I don't, they're taking liberties by saying that. Mesophyll cell. Mesophyll cell, basically, I'll tell you really, if this were a leaf and you're looking at the upper epidermis and the lower epidermis, all the cells that you have between the upper and the lower, most all of them, not all of them, but that's middle filling. They're all mesophyll cells. So when they say this is a mesophyll cell, I'm like, yeah, well, it would be somewhere in the middle of that leaf. I do agree with you there. But can't you come up with something a little bit more specific to call it? It's a cell in the middle of a leaf. It's a cell in the middle of the leaf cell. Yeah, well, thank you for that. That really helps us to understand something. Yeehaw. Aren't you writing a great biology book? No. let's call it the soft G cell. Give it something specific. Goodness. Mesophyll cell. That's stupid. Anyway, we've got a 3-carbon molecule in here called PEP. And yes, that's just an acronym for PEP. Okay, let's write it here. PEP. PEP stands for, you're going to love it, phospho. Of course, my brain works faster than my hand. Phosphoenol pyruvate. Oh, remember that for Scrabble. Phosphoenol pyruvate. Probably isn't going to have any. I can't use that for anything, right? You can win Scrabble here. Place a bet. $100, I can beat anybody at Scrabble in this room. I'm not actually saying that because I wouldn't pretty much put $100 down on pretty much anything. Now, a lot of people will. They love to gamble. I'm not a big gambler. If I go to Vegas, I would rather take say $100 and convert it all into quarters, and then stand in the middle of the casino and just pitch those quarters everywhere. Just pitch them everywhere, and watch everybody just scrambling on the ground for those quarters. Just watch them scrambling. That would be so much more fun than putting them into a machine or something. You know, that's how I would do that's what I do with my 100 instead of giving it to the casino. Like here, I'm placing the bet right here. 100 right here. Nah, throw it in the, just throw it around. Watch people scramble. Oh, a little entertainment out of it. Go see a show, you know. Tons of shows there you go see. I saw Joan Rivers there. God, that was great. I'm so glad I really got to see her in concert, the real deal. She was so incredibly filthy, I can't even tell you how much I loved it. It was so much fun. You know, it was just too hysterical. I can't even tell you. I still remember a whole bunch of the show verbatim. And I'd love to be able to tell you about it, but it was too funny. Anyway, some of the things she would do, gosh. The world, many of us really miss John. That was a big loss, for sure, for me. Absolutely. Too bad. Fashion Police, oh gosh. Golly, things she would come out with. Be like, oh man, you didn't just say that, did you? Can you say that on television? I don't think you can. But they were like, oh, it was Joan. Joan can say that. All right. Anyway, so we got this mesophyll cell in the middle of a leaf, special thing, and it has a PEP in it, a 3-carbon, and it combines with a CO2, and it forms a 4-carbon molecule. 4-carbon also has a name. So here we have the 4-carbon molecule. 4-carbon molecule is called an oxaloacetic acid. You know, and maybe I'm just as sick as Joan because I remember these terms. That makes me as sick as she was. I don't know. But what the 4-carbon will do will be to drop off the CO2, and then it will come back as a PEP, which then can pick up another carbon, form the 4-carbon oxaloacetic acid, and then drop off a CO2, and then go back out as a PEP, and pick up another CO2 and drop it off, and then come back out as a PEP, pick up another carbon and drop it off, and come back out as a PEP. So what you're doing is slamming a whole bunch of CO2s into this bundle She cell right here, where you're doing really the C3 path. You're just pumping a whole bunch of CO2 into the cell that does the C3. The more CO2 you can pump in here, the more sugar you can get out of it. And you just don't have one mesophyll cell here. Those things go all the way around this bundle sheath cell. So really what it looks like, if that's the bundle sheath cell, it kind of looks like a sunflower, because you have all these special mesophyll cells that are going around it. Every one into this cell right here. That cell is where they're pumping CO2. So you've got all of these mesophyll cells, which are these things. So all of those are mesophyll cells, and they're pumping carbon dioxide into that cell where you're doing the C3 path. That's the only difference. It's called a C4 plant. They can grow, grow, grow. Grow fast. Fast-growing plants. And, you know, that's kind of the new kid on the block. You know, we had C3 plants for a long time, and we didn't have any C4 plants. And then all of a sudden, C4 plants evolved. And now we've got plants that are just growing like crazy. They're growing really, really fast. And so the number of C4 plants that we're going to see in the environment is going to go way up. You know, and plants are just get mega huge. You know, you can see, you know, well, what if you had an oak tree that all of a sudden became a C4 plant? You know, what? You'd get like a 300-foot oak tree, and it'd grow in, what, 6 months? You know, man, could I build a treehouse or what? I would build a treehouse I could live in, you know, and just throw acorns at people. Not really. I would. I would. Yeah, I'd have battles with squirrels, right? You're in my tree. Yeah. Try to hit squirrels. I'd develop an acorn gun, you know. You just, you know, make one. It just kind of fired out acorns at these squirrels. I'm a 10-year-old up here. The body's 58. The mind is 10. I know, it's true. It is very true. Very true. I think on a 10-year-old level. In reality, you know, somewhere in my brain, all of this stuff is stored, but it's not in the 10-year-old part. It's in like a little, it's in a little section there somewhere. I don't even know why it's there, but I think it's fun too. I love that part of my brain. It just is kind of a cool part to know some stuff, you know. But then I have that other part that just wants to play all the time. Just play. Never serious. Just play. Yeah, I'm really a lot of fun if you get me out of school. Once I get out of school, it's like, okay, the handcuffs are off, or maybe they're on. All right, anyway. So one other thing I do want to talk about, and I've only got one other thing relative to this chapter, and can only talk about one other thing because we're out of time. Photorespiration, as if I had enough time to screw around and talk about this other building a treehouse, shooting, making a gun to shoot squirrels. I don't have time for that. I just find it's necessary that I make time for that. It's for me. It's not for you. It's just for me. Survival. It's a survival mechanism. I have no idea why. It just is. It's necessary for me. Okay. These are this is what's called photorespiration. Oh, I've got two things to talk about actually. Photorespiration. But they're kind of similar. Photorespiration. This is what our plants do in West Texas when it gets really, 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 really hot. A leaf which has stoma on it, the stomata there, those little kind of smoochy lip-looking things on the bottom epidermis, lower epidermis, where the carbon dioxide can come in, CO2 can come in, and the oxygen can get out of the plant, the excess oxygen. But the other thing that comes out, you know, not only just oxygen, but the other thing coming out of that leaf is water. Well, we don't have an abundance of water. Y'all figured that out. We're in a drought. We've been in a drought for a long time. Do I think we will ever get out of the drought? You probably don't want to know my opinion on that, but you can probably guess it. Do I think things are going to improve? You probably don't want to know my opinion, but you can probably guess it. And I'm not just being pessimistic. I'm just looking at the numbers. on that. But, okay, so, when it's really, really hot outside, we get to 100 whatever around here a lot. That means we are losing the concentration of water, the amount of water that's actually coming out of that leaf is tremendous when it is hot. Well, okay, we want to prevent that from happening, so we close these stomata. We close them off. Okay, so if we close these, that means we're not losing water. That's a good thing, but we're not getting carbon dioxide into the leaf. That's a bad thing. In order to make the sugar, the carbon dioxide has to combine with a 5-carbon to make the 6-carbon, so it can split to make 2 3-carbons. You add your hydrogens, you make PGAL. Put those together, you make sugar. Calvin cycle. All right, we can't do that. We don't have any CO2 coming in. So what they do on photorespiration, you're not getting oxygen out either. So the oxygen concentration in this leaf is going to go up. That's up. Concentration of oxygen is going to go up. So what they can do, instead of doing the CO2 plus the 5-carbon, they actually do this. The oxygen plus the 5-carbon RUBP forms really a 5-carbon with an oxygen on it. That will split. You can't split it into 2 3-carbons. That is, but you can split it into a 2-carbon and a 3-carbon. So a 2-carbon and then a 3-carbon. To carbon, which is PGA, you can actually use your NADPH2 and your ATP, and you can form PGAL. All right, which is really your 3-carbon with your 2 hydrogens on it. All right. So, but if you do this 2 times, you can make sugar. You'll make 2 of these, make sugar. Okay, but you can do it a lot. You can do it not just 2 times, but you can do it thousands and thousands of times. You've got, it's very hot. You're making lots of oxygen. You can still do that. You can still do the light reaction. You have a lot of light. You can still do it. In fact, you can do a whole bunch of it, and you generate a lot of oxygen. You split up water, as long as you have the water to do it. You just want to conserve water. So around here, most of our plants do photorespiration. They close off the stoma during the day. So this is day, stoma closed, because it's hot. Really, the stoma is the whole. Stomata would be the little guard cells on each side that close it off. Stomata closed. But then at night, the stomata open because it gets cooler at night. So then they can get their CO2 in. So now, if you've got your little holes are open, then CO2 can get in. So then you combine the CO2 plus the 5-carbon to form the 6-carbon, and hopefully you know the rest of the story after that. So you make a lot more PGAL. But you do most of that C3 pathway, the 1-carbon plus the 5 to give a 6. It splits into 2 3s. You do most of it at night. You still can do some of it in the daytime because you're combining your oxygen with your 5-carbon. You can still make PGAL, but you're not making as much of it. So they make most of their sugar at night by opening the stoma late when it's cooler. So it's just called photorespiration. That's it on that. One other thing I do want to mention, some plants, really your cactus, and also like a pineapple plant, pineapples. These are what you call CAM plants, CAM, C-A-M, CAM plant. CAM stands for crassulacean acid metabolism. I know, you're welcome. You are so welcome. Crassulacean Crassulation acid metabolism, CAM plants. And examples of these would be cactus. Also, I mentioned pineapple. Not sure how to spell pineapple. Pineapple. Thank you. Pineapple. Okay. And what a CAM plant will do, will take a CO2 and combine it to a 3-carbon and produce a 4-carbon CAM, crassulation acid. And then they can release the CO2 from that. So it releases the CO2, and then you're left with a 3-carbon, oops, did that backwards. You're left with a 3-carbon molecule that will start that process over again. So then you come back to that. So it's just another way to actually throw carbon into the cell that is going to begin to produce your sugar, or that does make the sugar. It's just another system. Works really, really well. You find these plants typically in deserts. We're a semi-arid desert, at least we used to be in West Texas here, Odessa, Texas. But the Chihuahuan Desert is just kind of sneaking up past us, I think. At this point, we're probably desert. We're not a semi-arid. We're arid, which would be a desert. It's just going to continue to move forward and forward and forward. And at some point, maybe in your lifetime, maybe in your children's lifetime, it'll be past Texas into Oklahoma, you know, and continue to move further. And that's what I see happening. I don't really know. So at some point, I'm not really sure if I'll hang out anywhere near this area or not. Just sell out and just move somewhere north. Get out of the desert area altogether, just to make sure I'll have enough water so that I